Morning session and second lecture by Raphael Assier and Andrey Shanin. Raphael will speak again. So, please.
Yeah. Right, morning. Okay, so yesterday we somehow introduced the some ideas about functions of several complex variables. And in particular, we saw that singularities of such functions were lying on singular sets that were, in fact, for example, in C squared, two-dimensional objects lying in 4 dimensions. Okay, and then it's also clear from an application point of view that if we have in mind wave fields, well, it is for people working in waves and complex analysis, it's quite clear that wave fields often coincide with taking a contour of integration, say in a Fourier space or something like this, deforming it, picking up singularities of the functions, and as this results in some wave fields or asymptotic expansion of wave fields. So, of course, this is a motivation, and we want to do a bit the same thing with higher dimension functions. But due to the type of these objects, these two lines, this sort of two-dimensional unbounded object, it's not quite clear what it would mean to pick up the pole, if you wish, or pick up a singularity by deforming a contour. And in some sense, this set of lecture is aiming at giving us the tools to be able to understand what that means. Okay? And one of the tools that is important to understand this is the topic of this lecture, which is our second lecture, and this will be on differential forms, integration, and manifold. Okay. So for the exposition of this lecture, I will leave the complex plane for a moment. We will return to it in lecture 3 and 4, but we will do things in Rn. Okay, so we will for now. But the notions that I will discuss today are reasonably easy to expand to complex cases. Okay, so let us start. Well, first, I think many of you probably would have had a course on this kind of things at universities, maybe taught by people that are more expert than me in the topic, and probably this thing will form more than just one lecture. Okay, but I will try to summarize what I think are the important ideas that we should have in mind when thinking about this. Okay, so let us start just by explaining what we mean by differential forms. Okay, and in fact, it's often easier to explain what these are if we place ourselves in a given dimension. And since we were interested in C squared yesterday, we will, unless I specify that n is valid for any n, we will start thinking about R4. Okay. So, and in fact, we will create a set of definitions of things that we call forms. And in particular, so we can start with something that we call a zero form. Okay? Forms, we will use the notation omega, and they may be depending on some variables. So let's say A. And a zero form, what is it? It is just a certain function, A, where f is a function that goes from R4 to R. Well, you can imagine C as well, that wouldn't change much, but let's stick to R for now. And for the purpose of this talk, we will assume that these functions here are smooth. Okay, so you can think of f infinitely smooth. Okay, so well, you don't have to impose this restriction, but it's easier. We don't have to worry about loads of stuff if we do that. Okay, so basically zero forms are just functions, smooth functions. So this is reasonably simple. Now, one forms, there are objects, omega of A, again, that we can write something like this, F1 of A, dA1 plus F2 of A, dA2 plus F3 of A, dA3 plus F4 of A, dA4. Okay, so I just write that down for now. The question, obviously, again here, the fj are smooth function like this. Okay, each time I will use a function like this, fi, etc., there will be smooth functions on R4. And well, and we say that these objects here, the i's are, so if I take them all, a basis for the one forms. So in other words, I mean, each one form is a linear combination of things of that form, right? Okay. But obviously for now, I've said nothing about what these objects were. At the moment this is, and this is one view that is actually quite a good one to have something. View one, okay, the question is what are the DAJs? Okay, view one, DAI are just some symbols.
No meaning for the word basis.
Well, the word basis, I mean by this, in some sort of vector space type of thing, any members omega of the one form is a linear combination of something times dA1 plus something times dA2. That's what I mean by basis. Yeah?
Yeah.
And obviously this something lie in the space of smooth functions. Yeah? No. So this is one view, and in fact it's quite a good one to take. But we can be a bit more precise. And we can say that it's also possible to see them as they can be seen as linear functions that goes from R4 to R, such that, well, we can something like this, dA, say J, goes from R4 to R, and to a certain vector B, say in R4, I can associate a number that I can write like this. And this number is just something that we'll write like this, Bj, where the vector B, say, can be represented in R4 like this in now the A1, A2, A3, A4 basis. So this is useful here to now think about A1, A2, A3, A4 as some sort of coordinate system on R4, okay? So if you give a coordinate system in R4, then you can represent any vector in the column representation like this. And these objects here that are somehow associated to a coordinate system that we choose, I will talk more about this later, but they can be given by this. Okay. So that's a view 2. Okay. So we've got 0 forms, 1 forms, 2 forms. Let's go for 2 forms. So in particular, what does it mean? Here it means that if I use this notation here this should make sense, right? Okay, this first variable here goes into my functions, and the second, the bracket, goes into the little symbols. Yeah? So if I've got two forms now, we can define them as follows. Of A, dA1, dA4, plus the remaining terms, you would get the pattern. We've got then 2, 3 of A, dA2, dA3, plus 2, 4 of A, dA2, dA4, plus F, 3, 4 of A, dA3, dA4. Okay, so again, think of these functions as smooth functions on R4, and the question is obviously, what are these things? Okay, so what are dAj, dAi? Okay, right. So again, two views of these. View 1, they are just symbols, okay, that we pose and that we ask for them to satisfy such that define such that dAi dAj is minus dAj dAi. Okay, so I can say, okay, this is a set of objects I define to satisfy that thing. Okay, and in particular, you note that this somehow implies this. Okay, so if you have the two things. Right, whatever that 0 means in that set of symbols, right? Okay. View 2. Okay. This view 2, they are, we call them skew, symmetric, or alternate, bilinear functions defined as follows, so that you have dAi dAj goes from R4 to R. What am I saying? No. Goes from R4 times is bilinear, so I need. And if you take two vectors, B and C, then you have something like this. And again, this one now can be, applied to two vectors, and this is just going to be BI CJ minus BJ CI. Okay, and where B is B1, B2, B3, B4, and C is the same, C1. Okay, and it turns out that if you play with this definition here, you realize that what we've defined here coincides with the rules that we've created there. Okay, so you see the sign change, and obviously if the two vectors are the same, then if I and j are the same, then this stuff is 0. Okay. Right. Okay, so this now should allow us to define, and and so that means for two forms, this expression should make sense. Okay, so again, A is the variables that go into my smooth functions, and B and C go into my weird symbols up there. Okay, right. So this then, okay, I think we get somehow the pattern. That means I can define three forms. I will do it in less details from now on. Three forms. And I can define four forms, etc. So the three forms. So here, yes. So the DAJ can be thought of as a basis of these objects that are two forms. Okay. So now I would define three forms such that the basis is something that looks like this: DAI, DAJ, DAK, and from now we will sort of adopt view one. Okay, so I've hopefully convinced you that the two are fine, but it's easier to see these things as view one. Okay, where this thing, what happens if you exchange two neighboring one, you change the sign, and if two of them are the same, the thing is zero. Okay, so switch of two neighbors implies multiply by -1, and if I equal j or k, say this is 0. Okay. Yeah.
Is this multiplication associative?
So I will say something about this. At the moment, there is no multiplication.
Oh, no, but this is really multiplication.
Yeah, I don't need to introduce multiplication for now. I will in next page. So yeah.
Can you put brackets here?
Yes, you can put brackets here, and obviously these things will be, if I adapt the thing, multilinear, so trilinear functions on R4 that will be alternate as well. Okay. And so this is, in fact, and then you recover this thing. It's possible, same way to define that, but it starts to becoming a bit, okay. And at the end of the day, in all this sort of science, what you really use is there are these rules, okay. And same four forms, such that the basis now would be DAI, DAJ, and in fact, 1, 2, 3, DA4. Okay, because yeah. So if you think if I had two the same, that would be 0. So the only combination that is non-zero that I can get is something like that. And again, if I exchange two neighbors, I change the sign. Okay. So in fact, four forms are reasonably easy. They can always be written like this. A certain function times dA1, dA2, dA3, dA4. Okay? Right. And that's it. In the sense that now, if I carry on with playing with these things, well, if I wanted to define a 5 form, say I will need a basis made of 5 elements, but if I keep the rules that if two are the same, this is 0, then I cannot define any 5 forms. Okay, so if you have forms in Rn, say there's no such thing as n plus 1 forms in Rn.
The alternating tensor.
Yeah, this is very
same properties.
This is very linked to that. Yes. Yeah. Okay, and we can then just, for ease now of notation, we can say that we can write this thing here. Let's call this stuff omega curve Rn is set of k forms in Rn. Okay, so you can. So these are all the such omega, etc. Okay, so in our case here, the 4 forms here will be lying in omega 4 of R4 because we were in R4. This one omega 3 of R4, omega 2 of R4, etc. Okay. Right. So now I come to probably what you were referring to, which we will call the external product. Okay. So at the moment, well, this stuff for us are just objects, not pure notations whatsoever. And I want to see that we can actually make some sense of that little wedge there. Okay. So it's still linked to diffraction because we've got wedges. Sorry. Right, and this product we will define as follows. Well, in a formal way, you can take this operation and you go from, say, one set of k forms. Well, we can do it in Rn here times another set of, say, L forms, and that will take one k form and one L form. Okay, we have an idea of what we mean by this. And to these things, we can associate an object that we write like this. Okay, so the wedge product between omega 1 and omega 2. And in fact, this object here lies in the space of k plus L forms. Okay, and I will try to explain to you where that comes from. So, but before that, I need to give a few properties of it. I can find many such functions, but I will say, okay, property 1, we want that if omega 1 and omega 2 are of the same order, so by the order I mean the k there, then I want that omega 1 bracket wedge omega 3 plus omega 2 is equal to omega 1 plus omega 2 wedged with omega 3. Okay, so maybe this is what you were referring to. So I want this to be valid. Okay, and of course I've insisted that these two are of the same order so that I can make sense of this this plus, yeah, because we don't add carrots and onions, is it? Okay, and another one, property 2, I want to define this product such that if f is a smooth function and omega 1 and omega 2 some forms. The order here is unimportant. I want that omega 1 wedge with f omega 2 is equal to f omega 1 omega 2. Okay, so basically my smooth functions here, you can think of them as a scalar multiplication in that for that multiplication for that external product. Okay. So the good thing is, in some sense, it means that because of these two rules, the only thing I need to know in order to define it for all forms is to define it for every sort of small basis elements that we've defined, all the dAi, dAj, etc. Okay? So because of these two properties, it is enough to define it for basis elements. Okay, So I will give you a few examples on how you define it, and you will see it's well, it's not well, you would have guessed, let's say. So for example, if you have a one form wedged with a one form, yeah, all you need to know is that if you take a basis of a one form, so dAi, and you wedge it with a basis of a one form that is dAj, well, we say that this thing is given by dAi dAj, where now this was the just simple object that we've introduced earlier for these for the basis of our two forms. Okay, so we have them there. Okay, because when I introduced this object, I said nothing about the wedge in the middle. Okay, well, this is the effect of this operation. So you can see that this is a one form, this is a one form, and this, by our definition, is now a two form. Okay. So similarly, I will do two more, and then if you go from two form to wedged with a one form, then basically we only need to know how to do this dAi dAj. So this is a basis element of our two forms, wedged with dAk, say, which is a basis element of our one form, and this is by we define this wedge product here to such that this is okay. Right, and I can carry on like this. Basically, if I do a two form with a two form, I will have dAj, dAi, dAj, dAk, dAl, and I will get dAi, dAj, dAk, dAl, etc. Okay. Right, and then you can define some properties if you exchange. Okay, so I think if you get something like this, with this definition, you can show that this is okay. So when you switch the order of the product, then you get where m and n are the orders of the forms omega 1 and omega 2. Okay. Right, so you can check that it's valid for that thing. Okay, that's our external product. So it takes a form of degree k, a form of degree l, and it leads to a form of degree k plus l. Right, last bit of definition. There's something else, obviously, that we need to define now. Is here's that thing. Okay, so we will now be talking about this stuff. Differential of a form. Okay, so this is also called the exterior derivative. And this has this form, small d. Okay. So the one thing that you need to remember is that when we were defining our objects in the view 2, say somehow we established some links between these objects, these forms, and some sort of coordinate system, right? Okay. So now we will define, so we can define this. So we have, in some sense, when we write dA1, dA2, dA3, we have in mind a coordinate system A1, A2, A3, A4. So, and we will define this stuff again for various forms, but for a zero form, then you will all recognize something. So we have a zero form. Remember, this is just a certain function, yeah? And then we define d omega to be equal to, well, we can also write df, and df, unsurprisingly, should coincide with what we're thought it is at an early age. So this is df over dA1 dA1 plus df over dA2 dA2 plus df over dA3 dA3 plus df over dA4 dA4. Okay? Right, and so since my function f, I assume it to be smooth, etc., I don't worry about taking any of these derivatives. And this is, of course, the total differential of a function as we know it. Okay? And that's it, really, because now, okay, so again, we will assume some sort of linearity of this object. Well, I call it some sort of exterior derivative. So the derivative operator is linear, right? So this one we want to keep it linear, and so by linearity we can define d omega for any forms of any orders by just showing what happens to their basis, okay, or to the sort of basis element by d of a typical, I don't know which form I'm going to take, well, M form, it doesn't matter, f d a I 1 d a I M, say, okay, so an M form is made of the sum of these sort of things, of these objects, and this is just defined as follows: df, which we know what df is, we've just postulated here, wedged, but df, what is df? Is a one form, okay, so now I can wedge it with some other form, with dai1 DAIM. And this definition here, with what we've done, everything here is valid, right? I mean, everything makes sense. What I wrote here, I've got one form wedged with an M form, and in fact, we know what that is. This is just M plus 1, okay, form, and we know how to compute these things. Mm-hmm. And so this is interesting to see this operator D, in some sense, D takes elements of, well, M forms, say even in Rn, and returns something that is an M plus 1 form. Okay, so this effect of applying D to any form just increase the order of the form by 1. And the given form associate d omega, which is given by this definition here. Right, so independently of knowing what this means, we've just shown that we can at least define it in a consistent sense with the exterior products, etc. Okay, right. What's interesting is that these properties are valid. Okay, so I wanted to prove them by example, but I don't think I will have time to do that, so you should take my word for it. So if you take this object d2 omega, I define it as d of d omega, which I can, because if omega is a form, then in M form, d omega is an M plus 1 form, I can take its d. And this is always 0. Okay, so at home exercise. Take omega equal f dA1 dA2 in R4 and try to compute d2 omega. And you will see that this thing is indeed 0 just because taking partial derivative respect to one variable and then the other is the same as taking it the other way around on the Schwarz theorem. So this is quite a nice example to do. And what else do we have? Another one that will be useful for lecture 3 or 4. So if you take the derivative differential of a wedge product of two forms, then you can write it as follows. And omega 1 d omega 2, where omega 1 belongs to. Okay, so m is the order of omega 1. And in fact, this formula will be very useful later. So you can just at least convince yourself that all the things that I'm adding are part of the same space. Okay, so I'm not adding different things. Right. So, well, okay. We can. Whoop. There's other things that you certainly have heard of. And these are the notion of exact and closed differential forms. So we say that omega is exact if there exists another form omega prime, omega dash, such that omega is equal to omega is equal to d omega dash. Okay. Well, so if we find a form that is the derivative of another, we say that it's exact, and we say that omega is closed if d omega equals 0. That's the definition. Okay, so and from this definition we can have some very straightforward properties. I mean, they are not straightforward, but they are now that we've introduced all these.
Why do they call it exact? Exact derivatives, isn't it, more or less?
Well, yeah, I don't know. So if someone has the origin of that word, I'm happy to. Okay, so note, which is quite clear, is that any exact form is closed, right? Because see, if I write it d omega dash, then I take the d, I've got a d squared there, that's 0. And another one, any, say, omega belonging to. So if you take a form of the highest order possible, so you've got an n form in Rn, this is closed. And this is also going to be very important later on when we define what comes next. Not just next, but yeah. Okay, right. One last thing that I want to say, I've mentioned that things were linked to some sort of coordinate system that we chose. Okay. And we can change variables from one coordinate system to another. And in order to do that, again, the rule to do a change of variable is to have that if you change the variable from a1, an, say, to another set of coordinates psi1, psi-n, then you can relate these weird symbols as follows. Yeah, where J is the Jacobian matrix of your transformation. J is dA1 over d psi1, dAn over d psi1, 1, yes, I did it like this, dA1 over d psi n, dAn over d psi n. Okay? Right. And for example, if you have a form, if you have omega that is a one form in R1, so that's a classic situation, say omega is f dA, say, then it tells you that if I want to write omega as in a different coordinates, change of coordinate from A to psi, then this is just going to be f dA over d psi, Okay. And similarly, if I have omega is a two form in R2, then omega is of the form f dA1 dA2, and if I pass from A1 A2 to a different coordinate psi1 psi2, then I can rewrite this as follows: f is omega is f, determinant of the Jacobian d psi1 d psi2, and this can be done quite directly by using the fact that A1 now can be considered a function of psi1 and psi2. Okay, so I can consider A1 now as a smooth function, if you wish, of these variables. So you can do it directly. I won't do it here, but doing directly using that dA1, by definition, this is just dA1 over d psi1 d psi1 plus dA2 over d psi2 d psi2. Okay, so because I now can treat A1 as a function of the other variables, and if you stick that into this, use the rules of the wedge product, you will recover exactly that. Okay, but what's important is that a form somehow exists independently of the coordinate system it is defined in. Okay, and in particular, what is good is that you can exchange the derivative d and change of variables. Okay, so these two operations commute. Okay, so we don't really have to worry about that. Okay. Right. So this so far was some exercise, a bit of playing with defined symbols, etc., which, I mean, all have a very beautiful structure, but I want to talk about this integration. Okay. So, and we will take omega in being an n form in Rn. Okay, so the highest possible order of the form. Okay, so in coordinates, say psi1, psi-n, then I can write omega, which is f of psi d psi1 d psi-n. Okay, right. And now at some stage, if we want to define integration, we have to define something that we call orientation. Okay, and this. Okay, so define orientation epsilon as follows. We will say that epsilon equals plus 1 if integral of a certain, whatever that means, of psi1 then is positive. Okay, so basically, if it returns, if you think in terms of volume, when you integrate a certain volume, if this stuff returns a positive number, we say that the orientation is plus 1. It is minus 1 if it is negative. But to a certain extent, at that stage, this is pretty much a choice. Okay, so we have to fix an orientation, and we define it like this. So this is not the same stuff as that. Okay. But this, once we have this orientation, and in fact there's often, even in other areas of integration, there's often an ambiguity of the sign of the integral. Okay, so here this is done in that way. But so let omega be a cube in Rn. Okay, if omega is a cube in Rn, you can think, for example, that sort of object. Okay. Then in the coordinate system that we've decided, then by definition we can say that the integral of omega, the integral of a big omega of our form is this epsilon, earlier orientation there, times integral okay, and obviously you realize that I don't have any wedges here. Why don't I have any wedges? Because for cubes this expression actually makes sense, okay? Because each of the integration can be done one after the other. So this object here makes sense because I've chosen this stuff to be a cube. Okay, and so this is how I do that. And then once defined for cubes, then we just write any other object as some sum of cubes, etc., and then we define for all. Okay, I'm going quite fast here, but that's the idea. In some sense, when we introduce integration, even for one complex variable, we define it on rectangles, and then from rectangles we can do everything. Okay. But message. It makes sense, we can integrate n forms on n dim domain of Rn. Okay, so you take an n-dimensional domain of Rn, you can always write it, decompose it in loads of small cubes, and then you can define Right, but I want to do one. So one thing here is that take a cube omega in Rn again. Well, we've chosen orientation of dx I1, dx In. Okay. Well, here I will not again go into detail, but this, for a fixed orientation here, this implies an induced orientation on the faces of the cube. Okay? By a face of a cube, it means I can take, say, if I choose to fix one of these variables to 0 or 1, say if I've got the 0, 1, n, I fix psi1 to be 0, say that's one face. But I can fix 2 to be 0, that's another face. Okay, so there are faces of decreasing dimension in a cube of Rn. Okay, but so it means that on the face of the cube, and hence on this thing, which is in some sense the union of the faces of the cube. Okay, remember for the polydisk we had a decreasing dimension order of a boundary. This is a bit similar. But what is good is that if you believe me on that, which is not a trivial part at all, and I'm not claiming to have explained it well here, then what is possible to do is if omega is an n-1 form in Rn, so belongs to, yeah. Then, and omega is, and big omega is the cube, then we have the magic formula that you've all seen. Okay, which is the, also known as Stokes theorem. Okay, what do we have here? D omega, omega was an n-1 form, so this thing here belongs to omega n of Rn, right? This is an n form because I've added 1 to n-1. This is a cube in Rn of dimension n. This is a form of degree n-1, but that lies on some faces that are, if you wish, the main face is also of dimension n-1, and on the smaller face you can show that the integral doesn't lead to any number. Okay. Right. So basically, what I want you to realize is that this expression here makes sense. Okay. Right. I've got a big task ahead of me because and I will be brief and informal for what comes. Manifolds and integration. Okay. Right. So how to define a manifold in 1 minute is not an easy task, and without any technical knowledge, what I like is to look at this picture. So you have something like this, a manifold M, and what happens is that we define manifolds by neighborhoods. So M is a set of neighborhood. So a manifold M of dimension small m is a set of neighborhoods. So it means that I can take some subdomain of my M here, and such that this neighborhood, in some sense, can be attached to a neighborhood of Rm. Okay? And by attached, I mean there is an homomorphism between the two. Homomorphism is just a bijection that have continuous inverse and continuous function. Okay? And then, so we can define, so this is a very local definition of a manifold, but then if you can think of then another neighborhood that slightly overlap the other one, and is going to another neighborhood in Rn, but these two will be shown to be linked very smoothly, and so you can somehow define things on the entire thing there. Okay, so I apologize for the specialist of manifold theory. And so, but it's good because if M is locally like Rm, then I can define it with some coordinate system, at least in that neighborhood, with a local coordinate system. M. So locally, M described by some coordinate xi1, xi_m, say there is a coordinate system in Rm. Okay. And one thing that is important is that a manifold can live in higher dimensional space. Space, say, Rn with n bigger than m. Okay? Okay, so example. If you think, for example, well, the surface of my sheet of paper here, something like this, even if it has some folds, etc., locally I can always make it look like a two-dimensional plane, but this lives in three dimensions. Now, each point of that object here has three coordinates. Okay. Right. So this is also called an embedding, if you wish. Live-in. In the literature, people call it this. Another thing, surface of the sphere, say in 3D, or for those familiar with complex analysis, if you take just the Riemann surface of an analytic function, of a function with some square roots, etc., this is also a manifold, 2D manifold in 3D. Okay, so this would be right. Now, we are going to try to link this with what we've done before and the forms. So this is again not an easy task to do briefly, but I will try my best. So if you let omega belongs to, say, so an L form in Rn, and let M manifold of dimension M that is less than n. Okay, so we're in the situation I was describing before. So we assume that it is embedded in Rn. Then we can find, then in some sense we can find local chords in Rn that are then, say, xi1, xi(n), such that manifold M is described by xi1 is 0, xi2 is 0, xi(n minus m is 0. Okay, so in some sense, I fixed all these coordinates to 0. That means I still have m degrees of freedom, and that's the dimension of my manifold. Okay. So it's quite clear what a form omega of degree L is in that thing. Okay, it's a linear combination of my Wills object d xi I, d xi j, etc. So the question is, what is the form restricted to my manifold, and the way to do that is as follows. So remember that a form is a combination of objects that look like d xi I wedged by d xi j, etc. So this my form omega is looking like this: a sum, if you wish, of fj of fj of a j of d xi I1 d xi IL, right? Something like this, right? And, well, we will just say that if you let omega dash to be omega, where we've removed all the terms that contain d xi I, where I is 1, 2, and minus m, okay? To be omega without terms containing xi1, xi(n minus m, then omega dash now is a form that only contains the degrees of freedom of my manifold, and we say that.
Is this obvious that you can always choose the basis so that the last so many are zero?
Well, the first one, yeah, well, I can, well, first of all, if you tell me it's obvious that you can choose m that are not 0 and the rest are 0, then I can always exchange the order with which I define.
Okay, the order is
but
it's whether you can always glue it up together. I mean, it's
so this is local, yeah, so this is true for a neighborhood that I've defined there, okay?
Right, okay.
So this is local for now. Now I've defined this locally, if you wish, on a neighborhood. I can define with this my form on a neighborhood of that manifold. But now the trick is to define it globally on the manifold. And in order to define it globally on the manifold, you do what the image is up there. You take a neighborhood that somehow overlaps your stuff, you pass from one to another, and then you use the trick of change of variables between forms. It's possible. It's not trivial at all. But this is how this thing is made. Yeah. Okay. Right, and I have. I guess I will be able to do them. Now, there is one thing that we came to call the secret theorem, and not because it's unknown, but it was unknown to us, and then we couldn't find it explained anywhere apart from as a footnote in one of Fam's book and mainly on internet discussion forums, which can be very useful.
Raphael.
Yes?
I didn't understand. Omega restricted to the manifold is defined as the omega prime.
Yeah, which is the definition of omega in this coordinate system here, where you slash all the terms that have a psi that I've set to be 0 here.
So it's just a definition of omega prime.
Yes.
Yes.
Yeah, and that's what I call the restriction. So I have something that this is what I call the restriction of omega. And this one is this, that if you take the derivative of this is the same as this, okay? So it's a bit tricky. Why is it tricky? Because here, this object there is a derivative from on Rn in some sense, well, this one, this thing, no, it doesn't work the same way. Okay, so these two objects are not exactly the same, but it turns out that you can do that. So this allows to write the restriction of d omega into a manifold without any ambiguity, because well, which one you take first is unclear, but okay, I'm not proving it here, but this can be done using the local coordinates things. Right, I'm almost there. Okay, so now if you take M manifold of dimension small m, and you take omega, set omega in M such that dim of omega is equal to m, then and small omega is an M form in Rn. Okay, so
And minus what?
not yet actually. I just want to define what this is. By definition, because here I integrate now not on a subset of Rn, but on a subset of my manifold. Okay, so this, by definition, I will say this is the integral of this, the restriction of my form onto the manifold, and this then makes sense with what we've done before. And the n minus 1 comes now. And this will be the last board. Let M manifold of dimension M, omega included in M, such that dim of omega is also equal to M. So you can think think always when you think of this, I mean, I find it easy, you think surface of the sphere and a small patch on the surface of the sphere, right? So, then, and omega, small omega to be an m-1 form on Rn, n bigger than m, okay? So you have this smooth embedding. Then, okay, all this to get to this. The integral over the boundary of omega of the restriction of my m-1 form to m is equal to the integral over omega of the exterior derivative of the omega restricted to m, in the sense that because we know that now this stuff makes sense. Okay, so we relate these two. Right, and this is the, I don't know how the generalized Stokes theorem. Okay, now,
Raphael?
yep.
Is n greater than m in that definition as well?
Well, yeah, because, yeah. Well, because otherwise this doesn't make sense. There is no such form, m form in Rn if m is not less or equal than n. Okay, right, so we've gone through loads of technical details to get to a super small formula. So I need to convince you now that that was worth it, and and I will do that. So what have we gained to do that? First of all, and this will probably speak to many of you, all the known integral theorems that we see at universities, they are special cases of this. Okay, you pick your m, the various different values of m and n. So if you take, say, the divergence theorem or Gauss-Ostrogradski theorem, it's the same thing. This is a special case of that. If you take Stokes theorem, as we see it on, is a special case of that. It has obviously a lot of applications. So in electromagnetism, divergence theorem and Stokes theorem are linked to the Gauss and the Ampere law. You can also, Andrey, I didn't think of that before, but Andrey made me think of that. If you think of Archimedes' principle as well, well, this is in some sense the divergence theorem. You've got a force acting on the surface and the volume, right? So you link some integrals, and that works like this. So this is very interesting for that point of view, but for the purpose of these lectures, what is great is that now we have some sort of machinery that allows us to first describe what we mean by our two lines, etc., our weird polar set, branch set, all this stuff, and more importantly, we now understand what it means to integrate stuff on that. So we can now think of performing some sort of integration on a polar set or on a branch set or something like that. And this is the basis of the generalization of residue theory from 1D complex analysis to ND complex analysis. Okay? So the notion of a residue, and that will be the topic. Is it next lecture? Or then, yeah, next lecture. We will see what a residue are and how they are important for, well, describing analytic function. We know that they are very important in 1D, but they're somewhat simpler in 1D. Okay. Yeah, so I think I've covered what I wanted. So sorry for the 10 minutes late.
Let us thank the speaker.
Thank you.